Hello. So is there a laser pointer on this thing? Oh, it's working well.
Okay, so welcome back again for this last second session of this morning. And our speaker is Kirone Mallick from CEA in Saclay. And he will talk about exact crossover in the Loschmidt echo for free fermions. Please, Kirone.
Thank you very much, Gregory. I wanted to thank Sanjib, but he's not here yet. He was there. Okay, so you will convey to him my thanks. Okay. I wanted to thank Sanjib for his invitation. I'm really very happy to be here. I love this place. I remember that I gave a series of lectures maybe 12 years ago, and I loved it. I mean, I'm so happy to be here. And the atmosphere is great. So I will tell you about something which is a bit quantum mechanical, which is not my usual piece of cake, but okay, one has to do quantum mechanics anyway. And this is a common work with Yasser Bezaz and Dimitri Gongart from Birmingham, Paul Krapivsky from everywhere, Jean-Marc Luc from Saclay, and Sylvain Prolac from Toulouse. So I'm not a quantum mechanical person, so I'm going to be very basic for myself. I want to tell you about Loschmidt echo, which measure return probability, overlap probabilities in quantum mechanics. They play a bit the role of large deviations. That was one of our interests in that. This problem is related to a very well-known problem which was developed in the late 70s, early 80s by Grosswitten and Wadia. Wadia, who's here, of course. And then by reviewing this case, I will go to the initial problem and try to explain to you how, in a kind of impressionistic way, how we computed this echo for free fermions. In fact, I think for me, I mean, this is the first time I give the talk on this subject presently. And somehow building the talk helped me to understand better. And finally, I think the only interesting part of the talk will be the last slide with some open problems and concluding remarks. Anyway, so what's the Loschmidt echo? Well, the idea is that if you have an n-body quantum system, which is described by a wave function psi, which evolves like psi of t by a given Hamiltonian, you want to know after a time t how much the state psi t resembles the initial psi 0 that you have. So what you want to compute is this quantity L of t. So it's a probability, it's a square of an amplitude, and the complex amplitude is given by the overlap of the wave function at time t with the initial wave function. If you just insert the Hamiltonian operator and the evolution operator, what you want to compute is the square, the modular square of this matrix element. Okay, and that represents, again, the echo, how much the state at time t resembles the initial state. So one thing is that typically, it's not a theorem, this Loschmidt echo is exponentially small with respect to the size of the system. So in this sense, it is a rare event to resemble your initial state, and it resembles a bit the idea of a large deviation, but in quantum mechanics. And of course, as many of us are interested in large deviations in stochastic processes. Okay? So I'm going to try to compute only the simplest case of a Loschmidt echo. And as you will see, although the problem is simple, the calculations are not so elementary. So we shall consider free fermions on a one-dimensional lattice. A priori, you could do it in higher dimensions. And so it's a discrete lattice. And we start with an initial condition, which is a double domain wall initial condition that I denote by dw, where you put these n fermions from site 1 to site n, and the rest is empty. And then we just leave the thing evolve through this tight binding Hamiltonian, non-interacting fermions. So it's just hopping terms. You just make the fermion hop from n to n plus 1 or n plus 1 to n by hermiticity. And because they are fermions, these operators Cn satisfy anti-commutation rules. So that's just the rule of the game. And there's an energy scale here, J, that I will take equal to 1 by normalizing it. And again, the initial state is just the domain wall state where you have put initially fermions from 1 to n. And what we want to compute is the Loschmidt echo. So we want to compute this quantity, how much the domain wall evolves in time t and overlaps with the initial domain wall. There are two parameters in the system, the time, the evolution time, and the number of fermions n that you put initially in your game. And there's a unique dimensionless ratio, which is n over t, which I will call lambda. Of course, you will say there is a dimension here, but if you put back h bar and the energy scale j, this becomes a dimensionless number. And things will depend only on this dimensionless ratio, lambda, which is a kind of aspect ratio. If you put a time evolution vertically, this will be a kind of aspect ratio of your problem. And you will see that there will be a critical value of this ratio, lambda critical, in which there will be beyond and after which there will be a change of a feature, a quantitative, in fact, a dynamical quantum phase transition, as we shall see. So this is a non-interacting problem. This is a time translation, space translation invariant. So it can be diagonalized by Fourier space, and eigenmodes, and the energies are just given by the cos, -2 cos, and the Fourier transform operators, which are creation and annihilation operators of a momentum Q, they also satisfy the antisymmetric commutation relation. So everything is okay. Now, if you're completely allergic to quantum mechanics, which I can understand, you can just forget about, this is second quantification, so it's even second stupidity, as I think Einstein said something like that in more nice words. So if you don't really want to talk at all about these operators, anti-commutation, and so on, you can put this problem as a kind of, PDE problem. You want to solve an n-body Schrödinger equation without interactions, so it's just a kind of, discrete Laplacian. You want to find psi in an antisymmetric form. These are fermions, so you don't want, if two people sit at the same place, this thing vanishes, and if you permute two of them, you have the sign of the permutation, which comes. The initial condition is just psi 0, 1 to n is equal to 1. And what you want to compute is the square, because these are complex numbers, the square of the values of psi t evaluated at 1 to n squared. So forget about second quantification, whatever. It's just a PDE problem, if you prefer. OK. So now the first thing to realize is that this Loschmidt amplitude, so we'll first talk about the amplitude and then in the end take the square of the modulus. This Loschmidt amplitude, you can write it as a nice integral form, as a n-apple integral in the basis of the momenta. And you can write it like that. Okay? So I will just explain to you a bit later how this form comes. But what you have to compute is an n-fold integral of dq, exponential 2it cos q, and this modulus square of this amplitude. So how do you do that? Well, it's not so complicated. You just start with this initial matrix element, and you know that the Hamiltonian is diagonal in the Fourier space. So you insert the QQ basis, the Fourier basis, and when you insert it, H becomes diagonal, and the eigenenergies cos Q pop out, and you just end up with that. Okay, so that's elementary quantum mechanics. Now, if you look at you look more precisely at this matrix element, how the domain wall state 1 to n overlaps with Fourier modes, well, what you will see is that, again, we can invoke basic quantum mechanics. These are fermions, so you want to have antisymmetric wave functions. So you have to write a determinant, a so-called Slater determinant of these pure waves evaluated at numbers 1 to n. So what you end up with is that this matrix element of the domain wall written in the Fourier basis is nothing but the determinant of plane waves. Okay. evaluated at 1 to n, and for momenta 1, q1, qn. So now this thing is nothing but a van der Monde determinant. Okay? So this van der Monde determinant is just a product, van der Monde determinant of x1, xn, x1 square, x2n, xn square, and so on, is just the product of xi minus xj. And there is a model square here. So you end up with this nice expression for the amplitude of your Loschmidt echo. And this nice expression, of course, for people who work in random matrix theory, which is not my case, but which is the case of many people in this audience, it really looks like random matrix kind of integral that was studied by Mehta, for example, that you meet that you see in the field. Okay. So all in all, what we have to do is to analyze this object. It's a purely mathematical problem for a large time, for large n, and try to see how the asymptotics of these integrals look like. So there is a little step. So this is a nice representation of this amplitude, but you can massage it a bit by using a cute identity, which is called the Andreev identity, probably has other names too. And this Andreev identity tells you that if you have an integral, n-tuple integral of product of determinants, you can write it as a determinant of integrals. Okay? So this looks, when you look at this identity, it looks complicated or a bit bizarre, but in fact, it's very easy to prove. So for people who have never seen it, or students, I just encourage you, just write the definition of the determinant as a sum of the permutations of blah, blah, blah of your matrix. You write it twice, and you just, in 2-3 lines, you end up with this identity. And this will be very useful, because indeed, here, in fact, because of the modulus square, I have 2 van der Monde determinants, in fact. So if I just use my Andreev identity, I end up by a very cute representation of the Loschmidt amplitude, which is given by a determinant built from Bessel functions, remembering that indeed Bessel functions are the Fourier transform of exponential of a cos. And this is a classic definition of Bessel functions. So this kind of determinant is called a Toeplitz determinant. So again, name for something which is quite easy to visualize. It's a matrix which is finite with j zeros on the diagonal, j1's upper diagonal, j2 the next diagonal, j minus 1 in the lower diagonal, and matrices which has this structure, which are uniforms along their diagonals. They are called Toeplitz matrices. And these matrices have beautiful properties. In particular, their determinants can be evaluated when they become very, very big. They are theorems which allow you to understand how these determinants look like. So let's try to work that out a bit better. But before I do that, I would like to analyze, as I told you, I'm interested in large time, large n, large number of fermions, and I will try to work out special cases. For example, finite n and large time, or large n and finite time, and then come the real difficulty when both of them are large and their ratio is fixed. So let's do these little games first. So first of all, I start with a finite number of fermions, and I let them evolve for a very, very long time. So it's finite n and large time, and I can use a saddle point method. So I will not go into the details, but let's be a bit naive. So let's go back to this representation. So n is finite and t is very, very large. Okay, let's look at this. Well, what I want to do essentially is a saddle point analysis. And what will dominate, so again, n is finite and t is very, very large. Well, the Laplace or the stationary phase will come where the cos is stationary, so it means for q equal to 0 or pi, sine q equal to 0. Okay? So if I do this stationary phase method, saddle point analysis, for this finite integral, n equal to 4, 5, 10, large t, I can very easily see that the integral localizes around the values of q, which are either 0 or pi. Some of them are 0, some of them are pi. And then I can also expand around 0 or pi these, modulus squares. And I will end up with objects which look like that. Okay? And these objects are really, really the ones which appear in random matrix theory, and they are known. This integral can be computed exactly. You just take a classic book, Meta's book, you open it. It's a thick book, so you have to find the right page, but once you find the right page, you can just take the value of this integral. And in this integral, you have some power law behavior, but there is a nice function that appears when you compute this Selberg meta integral. It is a double factorial, product of factorials from 1 to n. This is called the Barnes superfactorial function. Anyway, once you do that, and you play a bit with it, you end up with a formula for the Loschmidt echo for a finite number of fermions evolving for a very, very long time. The formula is a bit strange. It is a little cute, or you can find it uncute. It depends on taste. Bizarrely, which happens is that the analysis for even number of fermions and odd number of fermions is slightly different. Okay, happens. This is a peculiarity of quantum mechanics. I mean, the large n limit distinguishes between even and odd. But anyway, what you see is that your Loschmidt echo decays as a power law. Okay, so if you wait a long time, the overlap probability decays essentially like t to the power minus n squared over 2, okay, or minus n squared plus 1 over 2. You have some prefactors, which are a bit similar, but they slightly change for odd and even. And essentially, now, if you take now, so we first took the large time limit with finite n, and now if we take the large n limit, so the limit of the Loschmidt echo taking first the large time limit and then the large n limit, we see that it's essentially, as I told you, t to the power minus n squared, but you have to do some, analysis of the factorials here by using Stirling formula, and you end up with a behavior which is exponential minus n squared over 2 log over t over n. So this is t to the power minus n squared, and this is Stirling, and you even have a 3 over 2. So this gives you the asymptotic of your echo in the regime where this ratio n over t, lambda, is very, very small. T very large, and n. Next slide. Yeah, next slide. So, but ask your question.
No, should be e to minus t squared. Huh?
It is. You already knew it. Pressed. Okay, so here it is, with a 2, because you take modulus square. Okay, exactly. So you want to do the seminar? Okay, so the opposite limit now, we put all the fermions from minus infinity to 0. We occupy the left side. We leave the right side empty. We leave this thing evolve during a finite time. But now we have an infinite number of fermions, and we want to see what is the probability for these fermions, I mean, again, hand waving, to go back to this domain wall state. And indeed, there's an exact result which is true for any finite time. Okay, infinite number of fermions, any finite time. The amplitude is exactly exponential minus t squared. The probability is exponential minus 2t squared. And this is a cute result by these people, valid for any time. And of course, if now I take, so this is first large n, and then large time, but this is true for any time. So this asymptotic in this region, in this sector, is given by an exponential minus 2t squared. And this is the sector where the ratio n over t is infinite. Lambda is infinite. Okay. So by the way, this is so there's, of course, as usual in StatsMech, it's not the first time you see that the two limits do not commute. There's a problem of inversion of limits. And you can obtain the result by using a nice mathematical result from maybe the beginning or the middle of the 20th century due to Zege, which is a general result for computing large size determinant of Toeplitz matrices. Maybe in the end I will tell you how this comes from. Okay, so finally, if you just want to match these two behaviors with the switching limits, if you look at that very precisely and look at that one very precisely, you can guess that the general form will be of the type ln of t is exponential minus n squared. I put a 2 here. some crossover function of lambda, lambda being n over t, and this crossover function f of lambda, or f of x, sorry, should be a lambda here, behaves like 1 over lambda square in one regime, and 1/4 log lambda, 1 over lambda, plus 3 over 8 in the other regime. I'm just copying the two extreme cases that I explained a while before. Okay? And now the game is, the question is, can we compute f of lambda for any finite value of lambda? Not only the extremes, but the crossover function completely. The reason is that this crossover function could be seen as a kind of large deviation function, or free energy, or call it what you like, what you want. So mathematically, it really boils down to a very specific and very well-posed mathematical problem. We want to analyze the asymptotics of this tuple determinant, okay, in the large n and large t limit, keeping their ratio fixed. And we want to extract the asymptotics of that. So why is it hard? I mean, it seems to be, kind of elementary problem. The source of difficulty is the fact that these Bessel functions are very highly oscillatory. So they don't behave so well. Yes? Yeah. Yeah, I'm pushing it completely, yeah. Well, it doesn't really matter because there is a translation invariant, but if in the finite lambda case, there are two domain walls. It's like a door, okay? And when lambda is infinity, indeed, it's like half. I mean, there's only one step. Well, you can put this finite n thing anywhere. Yes. Wait. So it's semi-infinite only when n is infinite. Then I really occupy all my lattice sites from minus infinity to minus 1 or to 0. But as long as n is finite, I have a bunch of guys which are sitting together, or girls, and they come back to their place. Yeah, one has to be careful with the he and his and her and she and so on. I try to be careful. Okay, anyway, so I was seeing Satya smiling. Okay, so let's be a bit hand-waving. So as I told you, I know the two extreme cases, and I want to see if something happens in between. So there's a cute analysis due to Jean-Marc Luc, in fact, where he used a recursion relation. So the thing is that, okay, these are these determinants. They have plenty of properties, and in particular, they satisfy a recursion relation, but a non-trivial recursion relation, a non-linear recursion relation. So this determinant, which I call an, if I define xn square by this ratio, you see it's a kind of logarithmic derivative, an plus 1, an minus 1 over an square. Okay, this thing goes to 1, so if I subtract 1, and I call this xn square, and then I call wn essentially the square root with an I to the power n. This wn satisfies a very cute recursion relation here, okay, with initial conditions which are given by the j's. And this cute recursion relation, I could not really trace back where it was written for the first time, but it appears in a paper of Borodin in 2001, but he cites also Bazor and other people. So this recursion relation, in principle, contains the whole information, because it allows you to compute these determinants very fast, much faster than just computing them brute force, and you can go to n equal to thousands very easily, with huge precision. And by the way, this recursion relation has a name. It's called discrete Panevet-2 equation, and it means that in underlying the structure of this determinant, there is some integrability, which is hidden. Anyway, so I'm not going to solve this recursion relation more precisely, but the analysis of Jean-Marc Luc goes as follows. If wn is small, we can kill the denominator here, and we end up with a linear recursion relation. But it's not completely trivial because you have this factor n over t, but this linearized recursion relation here, so now you change the book, you go from Mehta to Abramovich-Stegun, and you open it at the right page, And this recursion relation is nothing but the recursion relation of imaginary Bessel functions. Okay? So it means that if you just close your eyes and linearize everything, essentially the WNs are given by the INs, which are the modified or the imaginary Bessel functions, which do not oscillate, evaluated at time 2t. But we're interested in these imaginary Bessel functions for large argument and large index. And again, the asymptotics is very well known. And you know that these Bessel functions, imaginary Bessel functions, for large n and large t, behave like exponential 2t times some Lyapunov exponent, which depends on a factor theta. And the factor theta is essentially the inverse hyperbolic sine of lambda, lambda being n over t. Okay? It's just a parametrization. So when you look at that, you see that the sign of this object here will be either positive or negative depending on the value of theta. So either it's growing fastly or it's decaying fastly. And the threshold is obtained when tangent hyperbolic of theta is given by theta. So there's a critical value of theta, which means a critical value of lambda, for which, given by theta, critical tangent theta critical equal to 1, for which either this thing is growing or this thing is decaying. And of course, you can do this simple linearization only when it's decaying. So your simple heuristics here fails, of course, when theta is bigger than theta critical. So this gives you the hint that there's a critical value of theta given by this 1.196 and so on, which means lambda critical is around 3, exponential 1.1, for which the behavior between these two regimes should change. Okay? Again, this is not rigorous, or this is hand-waving. I will try to make that more clear in a while. How much time do I have left?
Sorry. You have a little bit more than 15 minutes.
Okay, good. Okay.
That predicts the good threshold.
This predicts a good threshold, which is going to appear as a broken heart transition. Okay, so let's back to classical physics, which is maybe more familiar and less tricky. And the classical physics, in fact, or the so-called Euclidean case, appeared in a completely different context of high-energy lattice QCD physics studied by Grosswitten and Spandawadia. So what is the classical physics counterpart of this problem? So forget about quantum mechanics. You take n random walkers on the lattice, and you subject them, how do you call it? You condition them not to meet up to time t. So you take your random walkers, and the only thing is that you don't want to touch each other up to time t. So this is, again, a very well-studied problem, and there is, in fact, a completely seminal, a beautiful paper by Michael Fisher in '84, which is called Walks, Walls, Wetting, and Melting. So I'm not such a good French. I should have said De Gennes, of course, but De Gennes introduced everything. So, and they have common papers in this area about demixing, also De Gennes and Fisher. So this problem of they are interacting. This random walker conditioned not to touch each other can be solved, again, by determinant formulas. In the math literature, it's called Karlin, MacGregor, Lindström, Gesell-Winnow determinant formula. Is the same thing as a Slater determinant in classical physics. And if you solve this problem, then you can again ask the same question: what is the probability that these classical walkers conditioned not to meet each other during time t come back to their initial positions? You can do the same type of calculation, same type of result. There will be, again, for a finite number of walkers, n and large time, there will be algebraic decay, now typically like t to the power minus n square over 4. Before it was n square over 2. Okay? And there is no odd-even effect here in classical physics. And now, as you could have guessed from the very beginning, the only thing is that you go from t to it. You go from real time to imaginary time. And instead of having a determinant representation of these J functions, Bessel functions, you get imaginary or modified Bessel functions, the I functions. Otherwise, everything is the same. And this problem was, again, analyzed by G, W, and W. And these people smart people, were able to compute exactly the crossover function for all values of lambda, and they found a third order phase transition for the value lambda equal to 2. So that's a very classic result, very old, 40 years old result or so, and very classic, 45 years old. Okay. And if I copy again what we did before, you can redo the same calculations. The only tiny difference is that before, for an, we had an I here, and now we don't have an I anymore. T has become minus IT. So one way to analyze this big integral is to write it as a kind of path integral and go to this Coulomb gas method, which is dear to Satya, Grigori, and other people in the audience. And instead of writing this integral as a finite integral, we go to n large. We write, I do it in a hand-waving way, but this can be done very cleanly. So you'll have here a sum of 2t cos k, which will become an integral of dk rho k cos k, where rho k is the empirical measure of the ki's. And here, if you take the log, you will have interaction terms with two rows, rho k1, rho k2, and log of modulus of exponential ak1 minus ak2. So you end up with a path integral representation of your return, classical return probability with this action. And what you want to find are the stationary path, the stationary densities, rho of k, in the Fourier space for this, that make this action stationary and which will dominate the asymptotic of your integral. Okay? So if you do that and just compute, the variation of the action, you will see that rho of k in this large n limit has to satisfy this integral equation. There should be here a Cauchy principal value. And this kind of equations has been studied a lot, for example, in hydrodynamics already at the beginning of the 20th century. And what you can see is that when lambda is large, of course, the interaction term dominates. So essentially, these k's will repel each other, and they will cover all possible values between minus pi and pi, or 0 and 2 pi. And when, on the contrary, when lambda is small, this term is important. So it means that, in fact, the k's will take the values around cos k equal to 1, so k equal to 0, or k equal to pi, cos k equal to minus 1, the stationary values that we had before. So if you do that, you see that for large values of lambda, the density, the stationary, the optimal density profile will spread over the whole interval and will take this form, which is the solution of this integral equation. And on the contrary, for small couplings, you will get this optimal profile, which was found by Gross and Wheaton in their paper. And the support of this density is not now the full interval, but it's a smaller interval between minus kappa c and plus kappa c, with sine square kappa c is equal to lambda. So in terms of interval, you have a transition where you have the full interval, which is covered in the large lambda case, and the part of this interval in the small lambda case. If you look at now how exponential ik, the phases are distributed, here they're distributed in the complete circle, and here only on a part, an arc of the circle. Okay? So all these are the results I'm just reviewing. And once you substitute these values of the optimal densities into the action, you get the two forms of the action. Lambda square is very easy to get with this formula. The other one is slightly more complicated, but you get the free energy in the other regime. And there is a third order transition at lambda equal to 2. So all these are very well known, and most of you have learned nothing up to now. The thing I want to tell you now is that these classic results are not so trivial to be analytically continued to imaginary time. It may look that you only have to substitute, put an I somewhere, but no, it doesn't work like that. So last thing I want to tell for this classic case is has been a recent reinterpretation by Pallister, Gangart, with whom we are working, Abanov in 23. And this is a cute reinterpretation of this Gross-Witten-Vadia transition. So if you take large lambda, which corresponds to this figure, so many n's, and time is fixed, it means that you don't have much time to make your fermions or your random walkers evolve, and only a few of them will walk, and the central region here will remain frozen. Okay? So what will happen, so these are density plots, space and time. So here you have the active region, but the central region of your domain wall will remain frozen, the yellow region, and nothing will happen there. The central guys will not have time enough to dissipate. On the contrary, if you have, let's say, the same amount of time, but a smaller number of fermions, then, of course, everybody will have time to evolve before coming back to its initial position. So this kind of transitions is known as a kind of Arctic circle transition, where you have a frozen region in one phase which exists, and in the other phase which melts. So it's a reinterpretation, and you have similar phenomena which appear in dimer tiling problems, in which they were first discovered by Trop, Shore, and other people, Elkis, and so on. Anyway, so in the last part, I want to tell you about the Coulomb gas calculation in quantum mechanics of the Loschmidt echo. How much time do I have?
You have 10 minutes.
Okay. So I will be a bit impressionistic, but I want to give you a kind of flavor of how the calculation went. So again, I'm rewriting the n-fold integral with now the I, which is here. Crudely, I rewrite it as a path integral for the density without really asking too many questions. The only difference with before is that now, in front of this external potential term, I have an I which is appearing. So the action now is a complex number. Okay? And if I naively write the saddle paths of this action just by copying what has been done by Grosswitten and Wadia, I will end up with a stationary or Euler-Lagrange type equation, which is the same as before, but I have an I. If I use the same solution, which is an easy solution for lambda going to infinity, so I just put the I where it was not, and I get a complex distribution of momenta. Okay? So what does it mean to have a complex density or complex profile? Well, if we go back to the finite n formula, it means that the kns now, they are going to wander into the complex plane. They are not going to be only between minus pi and pi, or 0 and 2 pi. They will start becoming, we'll have complex saddle points of this integral. And more precisely, so I have n wave numbers, k1 to k capital N, while the nth, the small nth kn, will satisfy this integral equation, okay? Because this is the density. So how many people I have less than kn? I have n of them. So it means that the fraction, the filling fraction, small n over capital N, is given by this integral. And this integral, if I keep the I here, is a complex number. So the meaning of this, I'm just doing this as a little exercise. The meaning is that if I call this function phi of z, which is z over, okay, there's a 2 pi which I put here. So it's z plus I over lambda, sine z. Okay? If I take this function here, I have to invert this function and evaluate it at fractions of 2 pi and find the value of k, which is now complex, because the function is complex, for which I get this correspondence. Okay? So phi is a complex function. I have to invert it and evaluate it on fractions 1 over n, 2 over n, and so on, and I get a path in the complex plane. The thing I want to emphasize is that not only you get an optimal complex density, but together with it, you get a path in the complex plane. And when you integrate this complex density along the path, you get integers. You get fractions, real numbers. So what we have to do is, again, not only to find the solutions of this kind of equation, but we have to find the corresponding path. So how does this work? So I'm emphasizing again, the complex optimal density comes together with the contour. So you have to compute the contour also, simultaneously. So when lambda is very large, it seems that this case is not too bad, even if I don't care too much about the fact that I have a complex I here. And if I use this optimal density to compute the action, indeed, I will get the value lambda square or lambda minus 2, which was found by a naive analysis. So I do get this asymptotic behavior in this large lambda phase. But the other solution that was found by G, W, and W, which is here, this one, the analytic continuation of this one doesn't give you anything. You really have to find another solution of your equation in the complex, in the imaginary case, which doesn't look at all like this one. So as I told you, in this lambda large case, if I put an I here, seems to be OK. But here, no way. If I put I here, I get something which is meaningless. So you really have to change gears and change the method. Okay? Naive analytic continuation does not work. And anyway, this is not clean. I mean, you cannot just put eyes like that and close your eyes and compute things. So the way of getting clean results is to use another technique, again, very familiar to people who work in random matrix theory, which is called the resolvent function method or the loop equation methods, which comes from RMT. So I'm going to go quite fast into it. I mean, maybe if there are questions, I can explain further. I rewrite my amplitude, but now using exponential variables. So this is just the same as before, just a change of variable. And what I notice is that I have still my von der Mondt square determinant here, and I have a potential, which is, the cos becomes z plus 1 over z, factor 2. And because of dk is dz over z, I have 1 over z to the power n, which I can put up there. So I have z to the power n, which is exponential n over lambda log z. So my potential becomes that. And if I look at the saddle points in terms of z of this n-fold integral, I find saddle point equations which look simply like that, just taking the derivatives. And here I have a log, so you take the derivative of the log. So these are the saddle point equations for finite number of particles in these. And the trick here, which I'm maybe not going to go into the details, is to study the resolvent, which means you study the function sum over 1 over z minus zi, which is a discrete form of the Stieltjes transform that Gregory told us about yesterday. And the beautiful thing, but I think I will just go very fast into it and not explain to you, is that if you massage this resolvent, you see the resolvent appears here also. So somehow these saddle point equations will imply some nice equations for G. And if you just play with it, and this is very elementary algebra, in fact, I gave it as an exam to my undergrad students 2 years ago, and some of them did perform well, not all of them. You get a very nice equation for the resolvent, which is a Riccati equation, which looks like j squared, 1 over nj prime, plus a linear term in j, plus a right-hand side, which is here. And in the large n limit, you can drop this term. This becomes just a second-order polynomial in j, and you can compute j exactly just by solving and using second-order equations. Okay? So you have determined this resolvent up to some factors, which are quite tricky, but you can compute them. And once you have the resolvent, by doing some manipulations, you can retrieve the value of your optimal density. So you can get the optimal density, okay, in a clean way. And all in all, your optimal density involves the square root of a fourth-order polynomial. So it's related to elliptic functions. So with that, you can really compute precisely the value of your free energy or your action or your Low-Schmidt echo. And one important difference with the case of G, W, and W cross within Wadia is that because you have elliptic functions here, you will have cuts, 2 cuts in the complex plane, and the contours will look a bit different. So now I'm going to be very impressionistic in the last few minutes. So this is what these contours that come together with the optimal profile look like for different values of lambda. Lambda smaller than this critical value, lambda equal to this critical value, and lambda bigger than this critical value. And what you can see is that here the contour is connected. For lambda equal to lambda critical, it has a crossing point. And for lambda bigger than lambda critical, the contour becomes disconnected. So this, from at least a pictorial geometric point of view, you have what we call a broken heart transition for lambda equal to lambda critical. And this broken heart transition is at the heart of this large lambda and small lambda difference. And you can analyze this picture more precisely, compute the free energy or this crossover function that I defined at the beginning. And what you can see is that near lambda critical, you have some logs appearing, which is not a big surprise. In elliptic functions, there are plenty of logs which are appearing. And these logs that are appearing show that, in fact, the second derivative of your free energy has a vertical slope at the critical point. So it means that, in fact, your transition is no more of the third order, but it's now of the 2 plus epsilon order, the 2 plus epsilon meaning that you have a log here. I'm going to finish. So now I want to tell you about a few open questions. I hope that some people will find it interesting to address. So I told you about return probabilities of free fermions or classical random walkers conditioned not to interact. So here are some questions which I find interesting, and there can be more. Can we start from more general initial conditions, not a domain wall? Can we interpret topologically this broken heart condition by looking at the underlying Riemann surface? So for elliptic functions, we have a torus. For the Gauss-Witten transition, this is a sphere. So what's happening to the torus when we go from imaginary to complex? We don't know if there's an Arctic circle interpretation in the quantum case. I told you about one in the case of classical random walkers. The fact that we cannot do analytic continuation blindly means that you have a change of behavior when you do the weak transformation from T to IT. So it means that somehow there's a kind of Stokes phenomenon in this functional space that we don't understand. We would like to do similar calculation for bosons, but bosons do not have determinants, and they are much more complex to deal with. I don't know what would be the classical analog to bosons. And here we really relied a lot going from quantum to classic. I don't know what is the classical analog to bosons. Of course, we want to add interactions. So instead of starting with the free fermions, we could start with the XXX spin chain or the XXZ spin chain, an isotropic spin chain. XXX is closely related to the symmetric exclusion process, the same way as free fermions are related to classical random walkers conditioned not to intersect. For the symmetric exclusion process, you can ask the same problem. We start with n particles in ZEP. You let them evolve, and you want to compute the probability of returning to their initial condition. For the half-infinite case where you put ZEP particles on the negative side and nothing on the positive side, the calculation was done by Derrida and Gershenfeld. And the return probability is exponential minus square root of t multiplied by zeta of 3 over 2 and so on. So, but the general crossover function for a double domain wall is not known. Amusingly enough, in the XXX spin chain case, where you put all your spins up on the left and all the spins down on the right, the calculation was done by Stefan in the complex case, and the result is the same as in the Derrida-Gershenfeld classical case. So here again, there seems to be a good correspondence in analytic continuation, but I presume that if you start with a finite number, it will not be the case. We don't know how to understand that. And ultimately, it's good to do calculations at the combinatorial level, but it would be nice to have something like a hydrodynamic descriptions for quantum echoes, like we have the MFT description for large deviations, for classical interacting systems. Thank you for your patience.
Yeah, thank you very much. We are a little bit out of time. Maybe a single question.
So do you see signatures of this transition in the density profile of the fermions? If you take some large number of fermions and evolve in time, there's a clear plateau at t equals 0.
Yeah, exactly. So that's what we are missing yet. We would like to have a kind of Arctic circle interpretation in the fermion case. Okay. It's very clear in the random walker case, and this has been computed. In the fermion case, we don't exactly know what kind of quantum observable we should compute to train, but there is certainly one.
Okay, thanks.
Yeah, I cannot resist to ask. Oh, you had a question? Okay, please.
Yes, so in the classical case, yes. But we are not able yet to compute it in the quantum case by inserting this C dagger C. That's something we want to do. But yeah, probably it will work.
Yeah, I cannot resist to ask you this question that for the classical Gauss-Witten-Wadia transition, around the transition there is a pain levé 2.
Yeah.
Here, do you expect also some pain levé 2 or something analog? Yeah, you don't know.
It's another question to
Yeah,
add in the
okay,
last.
yeah, okay.
I don't know.
Okay. Okay, thank you. Thank you very much. Let's thank Kirone.